Danger is everywhere. Countless asteroids, comets, space rocks, they're all around us. Earth is on a galactic shooting range, and we're the target.
We might have made it safely to 2013, no thanks to you Mayans. But we need to know where.
Where?
We need to know when.
When?
We need to know how likely that some far-flung space rock decides to level planet Earth.
Thankfully, a mathematician from the Far East.
Far East?
Chopsticks?
Ah. Well, we're Shasta High School's Shot Box team, and we'll be giving a brief explanation of Kepler's laws of planetary motion. So Kepler, who was in modern-day Denmark, was looking up at the night.
Actually, a man by the name of Tycho Brahe was looking up at the night sky. Tycho was engaged in the task of taking precise mathematical measurements of the movements of the planets. Why?
Well, I think it was OCD.
No. I think you need to imagine a world where there were no digital distractions. The best show happened at night, and it was in the heavens. For eons, humans had noticed that some celestial bodies did not move with the vast majority of them. The Greeks called these moving bodies planets, which means wanderers. Tycho set out to record the location and movement of these wanderers. Johannes Kepler worked with Tycho, and he wanted the data desperately, but Tycho wouldn't have anything to do with Kepler. Fortunately for Kepler, Tycho died. But Tycho's estate wouldn't give it to him either. So Kepler did what any well-intentioned 16th century mathematician would have done. He broke and installed it.
So now Kepler had all the information he needed on the motion of planets. So he went out to prove once and for all that he, as he believed, that the planets orbit the sun in perfect heavenly circles, which brings us to his first law, that planets revolve around the sun in circular orbits.
No, in fact, try as he might, he couldn't get the data to line up correctly with circular paths. So he looked past his preconceived notions and let the data and mathematics guide him to the truth. That celestial bodies actually orbited in ellipses with the sun at one foci.
So ellipses. These are these kind of weird cousins to circles that will typically get looked over in your introductory geometry course. But what's special about ellipses is that the sum of the distances from any point to the two foci are always constant. In this particular diagram, those distances are always 15. So in order to understand the trajectory of some apocalyptic asteroid, we need to know the parts of an ellipse. So first, we start with our elliptical orbit. The sun is at one focus. So this short distance from the sun to the nearest point on the ellipse is the perihelion. Its inverse, from the sun to the farthest point on the ellipse, is the anthihelion. And after you average these two distances, you get the semi-major axis. Now this is important because if you go from the sun to all points on the ellipse, the average distance from the sun is the semi-major axis. So when we're talking about orbits and planets, its radius is the semi-major axis. All right. Step 2, you need to understand eccentricity. This is defined as 1 minus the perihelion over the semi-major axis. So it gauges if it's circular or very spread out. For a perfect circle, the two foci are on top of one another. The perihelion and the semi-major axis are the same thing. You get 1 minus 1 is 0. So a perfect circle has an eccentricity of 0. With this particular ellipse, they're fairly close. The foci are fairly close together. 1 minus a large fraction will give you a small decimal. For something more elliptical, where the foci are spread apart, 1 minus a small fraction, 12 over 42, will give you a large decimal. So let's look at Earth. Eccentricity of 0.02. So that's pretty much circular. It's even more circular than that particular ellipse, which means that the perihelion and the semi-major axis are very, very similar in length. So the Earth never gets closer or farther from the sun along its orbit, pretty much.
So compare that to something like Halley's Comet, which has an eccentricity of 0.967. Something like that has a very wide swooping orbit. Most of the planets have very circular orbits, as Adam just stated, which is why it took so long and such precise mathematical observations for someone like Kepler to realize that they were actually ellipses. Kepler used Mars as his point of reference, and since its eccentricity is 4.5 times that of Earth, and its orbit is relatively fast enough that so someone could take multiple measurements within their lifetime, it was an ideal candidate for him to get to work on. So that's Kepler's first law. Kepler's second law states that two arcs swept on equal times by planets orbiting have equal areas.
Wait a minute. We have arcs in space, but a radius is on an ellipse. How does that all work together?
Well, Kepler didn't quite understand it either, but let's look at a demonstration of what he observed. As you can see by the scientifically precise diagram, as the Earth gets closer to the Sun, it speeds up, and as it gets farther away, it slows down. The mathematics explaining this odd speed change wouldn't be realized for over 100 years until Newton came along.
That's right. Newton realized that this speed change was actually a byproduct of the conservation of rotational momentum. Now, rotational momentum is equal to mass times radius times degrees per unit time. So as the planet gets closer to the Sun, its radius decreases, so the degrees per unit time has to increase, because the mass and its momentum stay the same. So what's important here is that that product, radius and degrees per unit time, has to stay the same, although their individual numbers will change. So how does that get back to area? Well, for that, we need to consider another formula. So here we have Newton's thinking that the mass stays the same, so that product, radius times degrees per unit time, at any 2 points on the ellipse have to equal each other. The important thing is that that product is constant, so we're going to write it as c. Now, the area of an arc is radius times degrees. It's that angle times the radius that you're going out. So if we make this per unit time, we get that the rate of change of area is equal to the radius times the rate of change of that angle. Doesn't that look familiar? It's our c. So the area per unit time has to be constant. So given two equal times, we're going to have equal areas. And that is Kepler's second law.
Kepler published his third law well after the first two, having discovered it later. But this is the single most important law in avoiding the asteroid apocalypse, as opposed to the much more personal and painful hemorrhoid apocalypse. But Kepler's third law states that the radius cubed is proportional to the orbital period squared. Wait, can I get that in English?
Sure. Write it like this. So the radius cubed is proportional to the period squared. So if we tried to solve for this in a physics way, we get a really ugly constant because we have meters cubed, we have period squared, we have it's seconds and meters, and it'd be terrible. So we made ourselves a shortcut. Instead, we just compare everything to Earth. So we get astronomical units, that's Earth's average radius, over years, that's Earth's orbital period squared, equals 1. Now that's elegant. We can plug in one value and solve for the other.
So remember Halley's Comet? It comes around the Earth once every 75.3 years. So from that, we can solve for its average distance from the Sun using this simple formula. If we plug in the years, we get that the astronomical units cubed equals 75.3 squared. So the average distance from the Sun equals the cubed root of 75.3 squared, which I'm sure you know is 17.8. So using this simple equation, we can find out that the average distance from the Sun of Halley's Comet is 17.8 astronomical units. Now something like Halley's Comet has a very eccentric orbit, so sometimes it's much closer to the Earth when we can see it, and sometimes it's much farther away, going up to 35 astronomical units. So why do we care?
Why do we care? Evan! We care because remember that little event in Russia last month? That explosion? Remember Siberia, 1908? That forest leveling explosion was just a little hiccup in universal scale. Siberia, that made little boy look like a little boy. We need to accurately be able to know where we are going to be and when we're going to be there if we're going to avoid planet Earth being just wiped to pieces.
So don't fret. Rest easy at night, my friend. Thanks to Kepler, Newton, and modern technology, when we identify objects in the night sky, we know where they're going and if they're coming here. Thank you.